Let's say you got alkyl halide. The first step is treating lithiums. That's going to make organolithium first, replace the halogen with the lithium. That's what it does. Second step, to treat the cuprous iodide, we'll make a dialkylcuprate. You got 12 days connected to copper, but now that this is a reaction segment, right? Not the other part. That's the part is going to be reacting with this carbon bearing the halogen. That's going to replace the halogen there. So all you need to do, just put them together. That's basically is that. You are having these 3 carbon chain, basically a little part from this part coming from that. You just make a bond between those 2 carbons together. So it's pretty simple. That's what we love about it. You can put things together. So this is kind of following the step. You give the step, you just have to follow as they are written, step by step, and then basically carry it through to the end. So predicting what will be the outcome of all the stuff. But question like this is kind of something that maybe puts you in the position that you have to figure things out. You can see here, we are studying for the benzene with the halogen there. Now the halogen is replaced by this carbon chain. After you just seen those dialkylcuprate, you can easily say that, yeah, that's basically what dialkylcuprate does. The carbons chains replace the halogen. It can happen even in the benzene, so this is basically perfectly what we just talked about. So based on the steps that we talked about, it can be easily done. You basically treat the lithium to this, then you're going to replace the halogen, whatever the halogen you have, with the lithium metal. So that's going to be the carbon ion, the phenyl lithium. You treat the cuprous iodide, that makes a diphenyl cuprate. Now that can be delivered to the carbon chain. The carbon chain has to be the one gets added there, right? So that's going to be this chain, the halogens are in. You can have chlorine there, you can have a bromine there, doesn't matter. But the thing is that these deliver there, and you just make the products. So once we know this reaction, the human reactions, then you know what to do. But sometimes people forget, right? Sometimes people just forget, oh, forget a copper. You may know, but you don't know how to use it. So if you don't remember that reagent, then you are basically out of know. No, you still can do these things, but you have to do it another way. So I'll let you show you. These type of questions is pretty much open-ended. You can have multiple right answers. So that's what I'm trying to show you. Let's say you probably don't know how to make a human, for instance, but you've been hearing so much about the making green one. So let's say we make a green one first. The bromobenzene, you treat it with basic magnesium metal, then the magnesium insert between the carbon and the bromine, so you get the phenyl magnesium bromide. That's a basic Grignard. If you're using a Grignard, based on attack to this chain, surprisingly, that does not go well. That does not go well. I mean, I'm always curious about why it doesn't go well, because we've been talking about the phenyl magnesium bromide is a good nucleophile. That's a good electrophile. It should make an attack, like I said, too. Should have replaced that, and we should get the same product form doing this way, combining these two. But surprisingly, the Grignard doesn't make an SN2. Even though you provide the primary of the halide, it still doesn't. So reaction with the Grignard reagents, I mean, we know how it behaves, but now we don't know everything yet. There's something that I still don't know why it doesn't happen, but the Grignard with the alkyl halide does make an SN2. If you want to make it like SN2, the copper is the way to go. That's the only way to make it happen. Organic lithium is another way. The organic lithium are more likely true carbon ion. They can actually make an attack and make an SN2 reactions, but not the Grignard. Grignards are very strange. So you cannot use this to make an attack with the reacting with this, but you have choices to make. let's say you have an aldehyde here. The same number of the carbon, but make that end with an aldehyde. The green, one thing the greener does really well is attack with the carbonyl. That's it's a specialty. So it attacks the carbonyl of an aldehyde really easy. This one makes an attack, you get an alcohol first. Of course, when you get an alcohol, this is not what you should have. You have to remove the hydroxyl. Now the question becomes, yeah, we can have all the skeleton carbons connected together. The problem is we have to get rid of the hydroxyl. Yeah, of course, if you have a molecular eraser, you can simply just erase it out. But unfortunately, yeah, we don't have the tool yet. So you have to find a reaction to get rid of the hydroxyl. So you gotta search your mind and what can we do to get rid of the hydroxyl groups? Then you probably remember that maybe we can think about the dehydration reactions. We are taking the oxygen off, but we are end up going to have a double bond. Because these hydroxyl groups are going to be protonated, and when this goes, there's a relief of carbocation, and then the base comes to take the protons away from this carbon, and then you get double bonds. That's basically just E1 elimination reaction. So if you do E1 elimination reaction, that's the reason you need a strong acid. Then you get double bonds, but at least we can get rid of the oxygen there. Now, the task is you have to reduce a double bond to single bond, which is pretty simple. Because we've been talking about the hydrogenation reactions. That is simply just a hydrogen gas with catalysts like palladium, nickel, things like that. So you can see here, I can accomplish the same thing, not using organocopper. I mean, there are probably other ways to make the same thing happen. It may take a little longer step, but if all the step makes sense, then it should work.